Hi, Abhay. Good evening. Okay, so let's wait a couple of minutes for others to join, then we'll start accordingly. So, Shikha, you got the recording links, right?
Hello, good evening, sir. Yes,
Yeah,
sir.
good evening.
Thank you so much.
Yeah, it's okay. I don't know why the recording links are not available in the portal yet.
Sir, your recordings are available, but not of week one. That's why I asked for
Okay,
particular week one.
okay. Fine. Okay, so I think we should start gradually, then in the meantime, others will join. I think. Okay, so today also we'll be solving a few questions from 2016 and 17 paper. Okay, so let me first share my screen. Okay, so this is question number 45 from 2017 paper, and the question says the diffusion limiting current, which is denoted by ID, at a dropping mercury electrode for an aqueous magnesium 2 plus solution of concentration C mole per liter is 300 microampere, and if C is increased by 0.1 mole per liter, the ID, which is the diffusion limiting current, increases to 900 microampere. So the value of C in mole per liter is, so we have to find the concentration of magnesium 2 plus ion in aqueous solution of magnesium 2 plus solution. So this question is on the topic of like polarography or the analytical method or electrochemical method. So let's first discuss some of the basics of polarography, then we'll be able to answer this question. Okay. So polarography is basically a type of electrochemical method of analysis. Okay, so it is the okay. So the in this method we use an electrochemical solution. In this case, let's say it is an magnesium 2 plus aqueous magnesium 2 plus solution. Then we use dropping mercury electrode, and we use another standard electrode. So the main principle is that we apply voltage between the two electrode. So first we apply voltage, between the two electrodes, one of which is actually working electrode, which we call the dropping mercury electrode. I will explain the term here, dropping mercury electrode, and another was is a kind of standard electrode. So why dropping mercury electrode? So this electrode actually we actually drop mercury through the capillary, and the electrochemical solution or the ions corresponding to the electrochemical solution actually absorb on the surface of mercury bubbles and mercury droplets, and then the electrolysis happens. So this is why we call it as dropping mercury electrode. So here mercury is generally dropped through capillary tube. So first we apply voltage between the two electrodes, then we measure the current flow between the two electrodes. Why current is flowing? Because when we apply voltage between the electrodes, then the electrochemical reaction will happen, or electrolysis of the electrolysis will happen, and because of the electrolysis the ions will generated, and the ions will go back and forth between the electrodes, and the oxidation and the reduction reaction will happen, and that's why the current will flow between the electrodes. So we apply voltage and we measure the current flow between the electrodes. So first we apply voltage, then we measure the current flow. So if we just plot the applied voltage or the measured current flow, which we call, let's say, I, and the applied voltage, let's say, V. So this is actually current flow, and V is applied voltage. Then a sigmoid type of curve will generate. So this type of curve will generate. So a sigmoid type of curve will generate, and this current, this we call the residual current. Let's say IR. This amount of current we call the residual current. Like this. And this amount of current we call the limiting current. So residual current means in the absence of any solution, just in the presence of just the electrolytic solution, which we, let's say, KCl. So in the absence of any particular substance or any particular solutions, there are some current flow between the two electrodes. So that's why we call it a residual current. So, and the limiting current is after applying a certain voltage, let's say after this voltage, the current flow actually reach a kind of steady state. So that's why we called it limiting current. And the difference between the limiting current and the residual current, which is this difference, we call it diffusion current or diffusion current here. So ID, call it diffusion current. So by measuring the diffusion current, we can measure the concentration of the given substance. Okay, so this method is actually used to measure the concentration of an unknown substance. So this graph is known as the polarogram, and the main equation here is we call it the Ilkovic equation, which is ILKOVIC, Ilkovic equation. And the equation is relation between the diffusion current, which is equal to 607 times N times D to the power half, then small m to the power 2 by 3 times T to the power 1 upon 6, then capital C. So this is a complicated equation. You don't need to remember this equation, just explain the term here. So N is actually the number of electrons involved in the electrolysis process, the number of electrons involved in the reduction and oxidation process. This is the number of electrons involved. Capital D is the density of mercury. Sorry, here, okay, the capital D is the diffusion coefficient. You don't need to remember this, so just small m is the weight of the mercury flowing through the capillary tube. Weight of the mercury flowing through the capillary, and T is the drop second, so drop time in seconds. And C, capital C is the concentration. Concentration of the substance, of the unknown substance. So to solve this question, we need to just remember the type of the equation. Here this is the diffusion coefficient, left side is the diffusion coefficient, and the right side here is the concentration of the substance. So from this equation you can just observe that the diffusion current ID, which is the diffusion current, is directly proportional to the concentration of the substance, right? This is the main relation we need to remember. So diffusion current is directly proportional to the concentration of the substance. Now let's get back to this question. So diffusion limiting current IG at the dropping mercury electrode for an aqueous magnesium 2 solution of concentration C is 300 microampere. So concentration is C mole per liter and the diffusion current is 300 microampere. Then we are increasing the concentration by 0.1 mole per liter and the diffusion current increases to 900 microampere. So we need to find out the concentration in mole per liter. So first, ID equal to 300 microampere when the concentration is C mole per liter. Okay, now the diffusion current increases to 900 microampere when we increase the concentration of the substance by 0.1 mole per liter. By means before it was C, then we are increasing by 0.1. So C, now the concentration is C plus 0.1 mole per liter, right? So now just use this equation. So ID proportional to C. So let's say ID1 equal to, let's say, proportionality constant, let's say K, so K times C1, then ID2 equal to same proportionality constant, now the concentration is C2. So this is equation 1, this is equation 2. Now from equation, let's just divide the equation 2 by equation 1. So ID2 divided by ID1 will be K will cancel, so it will be C2 divided by C1, right? So ID2 is 900 microampere, ID1 is 300 microampere, C2 is actually C plus 0.1 mole per liter, and C1 is C. Okay, so this is 3 equal to C plus 0.1 divided by C. If you just solve this, 3C equal to C plus 0.1, 3C minus C equal to 0.1, 2C equal to 0.1, and C will be equal to 0.1 divided by 2, right? So C will be 0.05 mole per liter, right? So the answer for this question will be, the value of C in mole per liter will be 0.05. okay, so to solve this type of question, just remember this equation and the relationship between the different quantities. So here ID is the diffusion current, ID directly proportional to the concentration, ID directly proportional to the concentration, ID is directly proportional to the number of electrons N. So these two properties are important, so just remember these two. So ID is proportional to the concentration and ID is proportional to the number of electrons involved in the electrolytic process. Then just use this type of relation and divide the equation 2 with equation 1, then you can get the value of concentration of the substance. So answer is actually 0.05. okay, so any doubts from this question? No?
Sir, please explain graph.
Okay. Yeah. So in polarography, so mainly we just plot the applied voltage in x-axis and the current which is flowing due to applying voltage between the two electrodes. So this is the current flow. Between the two electrodes in the y-axis. So if we just plot this, we get actually sigmoid type of plots. Like first we get like this, type of plots we will get. Okay, now this current value, this amount of current, we call it residual current. So residual current is generated because in the absence of any proper electrolytic solution, let's say here our main substance is Mg2+. So there are still some current will flow between the two electrons because in the absence of any proper substance, we to actually set up to, in our setup there are two electrodes first, and there will be an electrolytic, standard electrolytic solution which we call, let's say, NaCl or KCl solution. So due to the presence of K plus and the Cl minus ions, some residual current will be generated, will be between the two electrodes, so that's why we call it the residual current. Then we are applying voltage, right, along this axis. Then after some voltage, let's say after this amount of voltage, the current which is flowing between the two electrons will reach a kind of steady state. So in the steady state it will reach steady state when the diffusivity between the two electrodes, diffusivity of ions between the two electrodes, and the rate of oxidation or reduction at the dropping marker electrode will be exactly equal. So these are the details. So but just remember that after along this axis we are applying voltage, and after certain voltage the current which is flowing between the two electrons will reach a kind of steady state. So that's why we call this amount of current is limiting current. And the difference between these two currents, say this current and the steady state current, which is the limiting current, we call it the diffusion current. And the Ilkovic equation actually relates different quantities of our electrolytic solution with the diffusion current, amount of diffusion current. So ID, let's say, proportional to C, ID proportional to N, like this. Okay. So this is just the basic equation for in polarography. Y-axis is current flow and the x-axis is applied voltage, and the graph is called polarogram, and the nature of this graph is sigmoid. Curve. Okay.
Okay, sir.
Great. Then okay, so then just move to our next question. Just a second. Okay, so this is question number 23 from 2016 paper. So this is an organic question, a question for the organic chemistry, and this is the first time I am solving after a long time an organic chemistry question. Okay, so here the question is, the major product of the following reaction is, so this is actually furan, and the reactants is actually the acetic anhydride, and solvent is BF3 in ET2, which is diethyl ether, and the temperature is 0 degree centigrade. So we have to find out the major product in this reaction, for this reaction. Okay, so this is a heterocyclic chemistry question from the heterocyclic chemistry. So furan is, okay, the structure of furan is, so this is the furan, and when we are reacting with an electrophile. So electrophile means, let's say, E plus. E plus, which is the electrophile, that means the electron deficient substance. Electrophile means electron deficient substance. So there are mainly two possibilities. So let's say this is 1 position, this is 2, this is 3, this is 4, this is 5. Okay, so the electrophile can attack in two different positions, position number 2 and position number 3. Okay, so there will be two possibilities. One is attack at position, let's say, 2. Okay, so the lone pair will move here. Okay, so just attack at a position number 2 means here electrophile will attack here. So then it will generate here positive charge and here electrophile and hydrogen. Okay, now this carbocation, call this carbocation because cation on the carbon atom, so that's why carbocation. There are actually 3 resonance structures are possible. Like for this pi bond can move here, so there will be positive charge here and there is a double bond here, and then from this structure the lone pair of the oxygen can donate this electron to this positive charge and form a pi bond. So another structures are possible. Okay, so these are 3 possible structures. Okay, structure number 1, structure 2, structure 3. So if the electrophile attack on position 2, then these 3 possible resonance structures are generated to accommodate the positive charge. Now let's consider the case number 2 when attack at position number 3. 3 means here, so electrophile is attacking here. Hydrogen here, positive charge will generate, right? Now from this structure another structure is possible because this oxygen lone pair can donate this electron here and form a pi bond. Plus then here, then E, then H. Okay, so these 2 resonance structures are possible to accommodate the positive charge if the electrophile attacks on position 3, attack at position 3. Okay, so if electrophile attacks at position 2 of the furan structure, then there are 3 possible resonance structures are generated, and so to accommodate the positive charge of the carbocation, and if the electrophile attacks on the position 3, then the two possible structures are generated, resonance structures are possible to accommodate the positive charge. So we know that if the number of resonating structures increases, then the carbocation is more stable, because the positive charge gets scrambled over many structures. So that's why if the number of possible resonating structures correlates with the stability of the carbocation. Right? So if the number of resonating structure or resonance structure increases, then the carbocation will be more stable. So the carbocation generated by attacking after electrophile attacks the furan structure at position 2 will be more stable compared to this situation, right? Because there are 3 possible structures and there are 2 possible resonance structures. So that's why the carbocation is more stable here in this situation. So the product forming after attacking at position 2 will be the major product here. Now let's get back to our question. So here furan is given and the reactant is acetic anhydride. The structure is like this. Right? And the solution is BF3 diethyl ether. This is the solution. Okay. So now from this acetic anhydride an electrophile will generated like this. CH3 C triple bond O plus and CH3 C double bond O minus, right? Acetate ion and an electrophile. So electrophile attacks means actually when we are saying the electrophile attacks at position 2, that means the pi bond actually donates its electron from the position 2 to the electrophile. Okay, so just remember the term. So then the major product will be formed from position 2. We saw that. So the O triple bond C CH3 plus, so pi bond will attack from here. Pi bond will attack carbon atom and the extra electron will be towards the oxygen. So then plus, then this H plus will be generated from this, and then this structure will be generated. Plus this H plus will be this acetate ion will take the H plus ion and form the acetic acid. So major product will be this. This is the major product. And another possible product is if the electrophile attacks at position 3. Okay. So this is the minor product. Okay, so according to the question, so the option B will be the correct answer.
Sir.
Yeah.
Sir.
Yeah.
Number 2 and number 4 position are same, na?
Number 2 and number 4 position are same. Yeah. 1, 2.
So electrophile can attack and number 4 and 4.
No,
and
number 3 and number 4 are similar, and number 2 and number 5 are similar. Right?
Yeah, number 2 and number 5.
Yeah. Number 2 and number 5 are similar. So if the electrophile attack
Yes.
at 5 position, this is similar. This is the mirror image structure, right? So there is a perfect
So we
symmetry.
can get answer C.
Yeah, C we can get, because C, but the both position the electrophile attacking, and number 2 and number 5 also, right? But here the temperature is 0 degree centigrade. Okay, now if we increase the temperature from 0 to, let's say, room temperature, or I don't know the exact amount, if we increase the temperature, then the product C will also form, because in that case the electrophile can also attack at both positions, number 2 and number 5. But at 0 degree, only one position the electrophile will attack, only one position. The monoisomeric product will form like this.
Okay.
Okay. Okay. So the attacking of electrophile on both positions will depend on the amount of temperature we are giving. Because
Yes, sir.
Yeah, because at low temperature the reactivity will be slower, and if we increase the temperature the reactivity will be larger. Okay, so the option B will be the correct answer. Okay, I think everything is clear regarding this question. Okay, so let's move to the next question. Just a second. Okay, so this is question number 14 from 2017 paper, and this question is from the band theory of solids. Now in this question the energy band diagram for magnesium is given, or we have to find out the correct option here. The hatched and the unhatched regions in the figure corresponds to the filled and the unfilled region of the band respectively. Okay, so let's first talk about some basics of band theory. So now when molecule forms, any molecule form, the two atomic orbital or the different atomic orbital of different atoms will overlap with each other, and the two molecular orbitals will form, right? So we call it an LCAO method, which is the linear combination of atomic orbital. So let's say for hydrogen molecule, so the two atomic orbital of hydrogen atom, let's say 1s orbital of hydrogen atom will overlap with each other and two molecular orbital will form, right? We know this. So these are two molecular orbital MO. Now in solid, actually there are so in molecular orbital also we know how electrons will fill up, because electrons will fill up obeying the Pauli exclusion principle and the Aufbau principle, right? So the no two electrons can actually occupy a particular molecular orbital of same spin. So all the four quantum numbers will have to be different, because the electrons are fermions in nature. So that's why electrons has to obey the Pauli exclusion principle. So only two electrons can fill up here, one with spin plus up and one with spin minus up. So now in solids there are many number of atoms. There are, let's say, 10 to the power 23 number of atoms. It's a 1 mole case. So the atomic orbital corresponding to this large number of atoms will overlap with each other and form the n molecular orbital. So we know the number of atomic orbital. So in molecular orbital case, number of MOs will be equal to the number of participating atomic orbitals, right? Yes. So in solid case, in the case of solids, n number of atomic orbitals will overlap with each other, where n is very large, will form n molecular orbital, right? So from n atomic orbitals will form the n molecular orbitals, where n is very large. Now in general, for the H2 case, there is an energy gap between these two molecular orbitals, right? There is an energy gap. But when n the very large number of atomic orbitals overlap to form n molecular orbital, the energy gap between the two successive molecular orbital will be very small, right? Let's say when n atomic orbitals will overlap, the n molecular orbitals will form, let's say like this. Like this. So the energy gap between the successive molecular orbital will be very small, because n is very large here. So we treat this energy level diagram as continuum, right? So this is actually energy. So we treat this energy level diagram as continuum, because the energy gap between the successive molecular orbital is very small. So we treat this as continuum or continuous system. So this is why we call it as band. So that's from here the band theory of solid will come. So that's why this is called the energy band. Okay, now let's consider the sodium's case. So sodium, the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1, right? So let's say in the y-axis this is energy, and this is 1s, then this is 2s, this 2p, then this is 3s and 3p, like this. Okay, now the, let's say, in 10 to the power 23 number of sodium atoms, 1s orbital of sodium atoms will overlap with each other and form n, which is 10 to the power 23 molecular orbitals, and we will treat this as band, continuous band. Okay, so let's say very n 1s orbital of n sodium atom will overlap with each other and form a particular band, 1s band. Now how the electrons will fill up in 1s band? So in one sodium atom there are 2 electrons in the 1s orbital, like for one sodium atom. Now there will be n let's say there are n sodium atoms in Na atoms. So in n1s orbital there will be 2n number of electrons, right? Twin number of 1s electrons. So in the 1s band, so 1s band there are n energy levels, right? N orbitals, but they are very close to each other, but the number of orbitals is n, right? Because n atomic orbitals are overlapping with each other to form n molecular orbitals, n energy levels. So in each level 2 electrons can occupy. So in n possible energy level, the 2n total number of electrons can occupy is 2n. So in this 1s band will be completely filled up by electrons, right? Because there are 2n 1s electrons, and in 1s band there are n possible energy level. In each energy level only 2 electrons can occupy. So total n possible energy level 2n electrons can occupy. So all these 2n 1s electron will be filled up here in 1s band. So this band will be completely filled up. Now let's get back to a 2s case. So in 2s case, 2s atomic orbital of n sodium atom will again overlap with each other and form a particular band here, 2s band, let's say. And in the 2p case also, the 2p atomic orbital will overlap with each other of n sodium atoms and form a 2p band. Now observe that the energy gap between these 2s and 2p atomic orbital is small. So that's why the 2s and 2p band that will be generated will overlap with each other. So let's denote with different color. The white one is the 2s band and the yellow one is the 2p band. Okay, now in the 2s case also there are 2 electrons in the 2s orbital for one sodium atom, and for the n sodium atom there will be 2n electrons, and in the 2s band also total 2n electrons can occupy. So this total 2s band will be completely filled up by electrons. Okay, now in the 2p band also there will be 6 electrons in the 2p band, in the 2p orbital of sodium, one sodium, that is 6 electrons. So in the 2p band these 3 2p orbitals will overlap with each other to form 3n molecular orbital, right? In the 2p band there are 3n orbitals are there. So in 3n orbital total 6n electrons can occupy, right? So all the electrons will occupy here, all the 2p electrons. So this 2p band will also be completely filled up like this. Like similarly, like 3s and 3p band will also form. But again they will overlap because 2s and 2p energy gap is small. That's why the 3s and 3p energy level is still small. So that's why the 3s band and the 3p band will overlap with each other. And again the 3s there is 1 electron in the 3s orbital. Okay, this is interesting. So this is 1 electron is 3s orbital. Now in 3s band there are n orbitals or n energy levels. So in n energy level 2n electrons can occupy, right? But in 3s atomic orbital of sodium there is 1 electron. So for n sodium atom there is n electrons, right? N 3s electron, but the number of electrons can occupy is 2n, but the n electrons is available. So in the 3s band only half filled, so 3s band will be half filled just, and half will be empty for the sodium case. So this is the actually complete picture of the solid. And let's get back to our question. So this is, in the question it is asked the energy band diagram for magnesium. Okay, now just first define the electronic structure of magnesium. 1s2, 2s2, 2p6, 3s2, right, in magnesium case. So similarly this is energy. So just consider the 3s and 3p case. Okay, 3s and 3p case. So there will be a 3s band, and in the 3p band will overlap with each other. And let's say 3p band, oh, let's define with different color. So this is 3p band, and this is 3s band. Okay, so in 3s band, so in, let's say, n magnesium atoms are overlapping. So in 3s band total n energy levels are there, right? So in n energy level total 2n electrons can occupy. Right, or in 3p band also, in 3p band total 3n energy levels are there, right? Because in there are 3 p orbital, energy levels are there. So in 3n energy level total 6n electrons can occupy. Okay, now for magnesium case, for one magnesium case in 3s 2 electrons are there, right? 2 electrons are there for n magnesium, n number of magnesium case. So total number of 3s electrons will be 2n, right? 3s electrons. So for the magnesium case, the 3s band will be completely filled up, right? Otherwise in the sodium case there was one 3s electron for n number of sodium atom. There will be n 3s electron, so 3s band will be half filled, but for the magnesium case 3s band will be completely filled up. Okay, and the 2p band will be empty. So if you just observe the options here, so here option A, the S band and P band are not overlapping, but S band and P band will overlap with each other, so option A is wrong. Option B is also these two bands are not overlapping, so this is also wrong. And option C, these two bands are not overlapping, so this is also wrong. And option D, the S band and P band is overlapping and the S band is completely filled up. So that's why the option D will be correct answer in this question. So here the option D be correct answer. Okay. Any doubts? It is clear now why these two bands like S band and P band have to overlap with each other, because the 3s and the 3p orbital energy gap, this 3s and the 3p orbital energy gap is small. That's why when the 3s and the 3p orbitals of n number of atoms will overlap with each other and form a continuous band, then these two bands will also overlap with each other. So in here they are overlapping. But for other atoms, let's say the 3s and the 3p energy gap is very large. Let's say this is 3s orbital and let's say this is 3p orbital. The energy gap is very large, right? Now when these two orbitals of n number of atoms will overlap with each other and form a continuous band, then there will be a 3s band here and there will be 3p band here. They will not overlap, but in this case they will overlap with each other. And for the magnesium case, the 3s orbital will be completely filled up, and for the sodium case 3s orbital will be half filled like this. Okay, so the band theory of solids is actually very important to understand the conduction properties of metallic solids. Now we call there is a term conduction band and valence band. So valence band means the band up to which the electrons are completely filled up. Let's say this is a band, here electrons are completely filled up, so this is called valence band, and in here the electrons are empty, so orbitals are empty, energy levels are empty, we call it conduction band. Now to conduct free electrons, the free electrons has to propagate or has to move from valence band to conduction band. So when it is freely, when the electrons can freely propagate from valence band to conduction band, then we call it a conductor. Now in metallic case, like sodium, magnesium are metal, right? So they can conduct electricity. Why? Because look at this, the 3s and the 3p bands are completely overlapping. That means from the 3s valence band, electrons can move or propagate continuously here, right? So that's there are no energies needed to excite electrons to move from valence band to conduction band. So that's why the metals can conduct electricity easily. But for insulator case, there is an energy gap between the valence band and conduction band. Let's say this is valence band, this is, let's say, conduction band. So there is an energy gap here for insulator case. So electrons cannot freely propagate or cannot move from valence band to conduction band here. So that's why insulator, we call it insulator. So electricity conduction is not possible, or very large amount of energy is needed to excite electrons from here to here. Okay, now in the middle case there is a semiconductor. So in that case the energy gap between the valence band and conduction band is small, which is greater than the metallic case but smaller than the insulator case. Is small energy gap. Okay, so in this case, very little, by applying little energy or temperature, we can excite electrons from valence band to conduction band. So then this semiconductor can conduct electricity. So the example is like silicon, germanium, like this. So the semiconductors are very, very important, very, very useful in our daily basis. Like all the electronics items, you know, that the silicon chip, germanium chip is used. So conductor is very useful. Okay. And there are many research going on in the semiconductor field, in the high temperature semiconductor field, like how to prepare or how to synthesize a semiconductor which can conduct electricity at room temperature. So there are many research going on here. Okay, so in this case the correct answer will be option D. I think everything is clear.
So one example where energy gap between 3s and 3p will be large.
In a non-metallic case, like
Okay.
in any non-metallic case, we know, right, in the when you increase the atomic charge, when we go from left to right in the periodic table, the energy gap will increase. See, in that case, in non-metallic case, the 3s and 3p band will not overlap. Okay.
Okay, thank you, sir.
Yeah. Okay, then if everything is clear, then let's stop today and we'll meet in the next week, right?
Okay.
Okay, sir.
Okay, bye. Thanks for joining. Yeah, I am signing off. Okay.